So in this video, we're going to look at an example of how we can calculate the change in energy that's associated with just heating something up. This would also apply to cooling something down. The only thing that will change is what your initial and final temperatures are, whether it's positive or negative. In this case, it'll be positive. So let's look at the very first curve, part of the curve we looked at in the last video. And this is heating, and I picked a number here. Just we need to know how much snow we're talking about. Again, chemically this is H2O, but it's in its solid form, right? These are ice crystals that make up our snow. And so we pick a particular mass. This would be information you'd have to figure out, or it would be given to you, depending on exactly how the question is being asked. But the question that maybe you should be asking is, well, but how do I know how much energy it's going to take? And so one thing that is really important with this is that different substances have different ability to absorb energy. Whoops. So water, and even in different phases, the same substance in different phases has a different ability to absorb heat, and for that to cause a temperature change. So we can say, given if we have everything the same, different substances absorb different amounts of heat. And how we keep track of this is that each substance has what's called a heat capacity. And just as the name sort of implies, this is its capacity to absorb heat. So heat capacity, this is something that is like you'd have to get from a table, and these are often calculated as molar heat capacities. And this tells you how much heat per mole of a substance. There's another one which is, and so this is written as CP, or there's what's called the specific heat capacity, which is written as CS. These both are the same idea. It's how much energy, how much heat can a substance absorb before it changes its temperature. Molar heat capacity is given in terms of a change in, let me make sure I get my units right here, joules per mole times a degree Celsius, whereas a specific heat is joules per gram times degree Celsius. So the difference is that the molar heat capacity is how much heat is absorbed per mole of a substance, whereas the specific heat capacity is per gram. And to be more specific, this is to cause a change of 1 degree Celsius in that specific amount of a substance. So molar heat capacity is how much energy does it take to increase the temperature of that substance by 1 degree Celsius, whereas the specific heat capacity is how much energy does it take to take 1 gram of that substance, how much energy you need to put in to get it to change by 1 degree Celsius. So let's, we need this for water specifically, and specifically solid water. So if we go to a table, in your textbook you can look at table 6.1, but this will also usually be given to you. We can find values for water for the molar heat capacity. So water in its solid form, which is what's relevant for this question, is 37.1 joules per mole times degrees Celsius. Water in its liquid form can absorb a lot more heat. It's 75.3 joules per mole times degrees Celsius. And then gas phase water, water vapor, has a lower heat capacity again, 33.6 joules per mole times degrees Celsius. So what these values mean is that it takes 37.1 joules of energy to heat 1 mole of water, solid water, ice, up by 1 degree Celsius. So how do we use this heat capacity to actually calculate? We had our 270 grams of ice in the form of snow that we'd like to heat from negative 18 degrees Celsius, that was our starting point, to 0 degrees Celsius. So the way we calculate this is a pretty simple equation that we can use. Our delta H, or Q, if we assume this is a constant pressure, for this will be given by, we need to know the amount of substance we have, so this is number of moles, times the molar heat capacity, Cp, times the change in temperature. So here again, we're seeing this delta symbol show up. And this will be the heat associated with heating, in this case, or cooling, right? That change in temperature could be positive or negative. In this case, it's positive. So first we need to figure out from our 270 grams of ice how many moles that is. So if you plug that in and you can double check your work on this. But if you use the molar mass of ice, this works out to be about 15 moles of water, H2O in solid form. And the heat capacity is on our table over here. And we know the starting and ending temperature. So we can actually go ahead and calculate this. How much heat is associated with this. So Q is equal to 15.0 moles times 37.1 joules per mole times degrees Celsius. And then our delta T here, right, is T final minus T initial. Our final temperature is 0 degrees Celsius minus our initial temperature is negative 18 degrees Celsius. So we're going to end up with a double negative here, and that ends up being a positive. So our overall heat change here, we can plug all this in. This will end up being a positive 18 degrees Celsius, and then we can plug this into a calculator. The other thing you can see is that the units all cancel here. So, and we should end up with joules, which is our unit of heat. If we plug all that in, we get 1.0 times 10 to the 4th joules, or we can write that in kilojoules as 10 kilojoules. All right, but the main idea here is this equation right here, is that the heat or energy associated with heating or cooling something, you need to know the heat capacity, you need to know how much of the substance there is to be able to figure out how much energy, and then also what temperature change you're looking at. So this can be applied in multiple different situations, which we're going to see as we go into the future.